Okay, let's get started. A couple of announcements before we begin. First, there have been a couple of issues with the unit tests that I distributed earlier this week. They've been fixed, at least as far as I know, they've all been fixed. So if you haven't done so already, please go sync up the repository. Make sure you grab that new code that fixes those issues, and if you find anything else, let me know so that I can get that taken care of. It was my fault, actually. I uploaded the wrong copy of the file. I had one that was working, and then I just picked the wrong one. So sorry about that. That's my fault, but it is corrected. Go grab the new copy so that you've got the tests for homework 2. Homework 1 grading is going pretty well, actually, so far. We've made it, I'd say, about halfway through, so if you check your grade, there's like a 50-50 chance that it's there. If it's not there, sit tight. We're still working on it. Should just take us another day or two to get the remaining grades posted. So if you have any questions about that assignment, you're always welcome to come find me in office hours, or I can talk to you for a couple minutes after class maybe, if you have questions about your grade or anything like that. Are there any questions about homework 2 or anything else before we start talking about B+ trees today? Any questions? Okay, so today we are going to talk all about B+ trees. And again, I want to remind you that B+ trees are the focus of the next homework assignment number 3. So it's really important that you understand how these trees work, because I'm going to ask you to implement them in the next homework assignment. So we're going to take a look at what B+ trees can do today. Let's start off with the structure. This is a little bit of a review from last time, but it's important that we all understand these basic concepts before we start manipulating these trees. So we've got two kinds of nodes: internal nodes and leaf nodes. What goes in the internal nodes? What am I going to find in an internal node of a B+ tree? Yeah. Pointers, okay? So pointers to other nodes. What else am I going to see? What else? Yeah.
I guess, I don't know if it's storing the actual value, but you have to have something to index on so it can tell you go left way for...
Yeah. Something that tells us where to go. So we call those search keys, right? They're keys that we use for searching purposes. Which path do I want to take? Which child do I need to visit next? Look at the search keys, and that will tell you. And then we have the leaf nodes. What's in the leaf nodes? Yeah, go ahead. Go ahead. The real data, which in this case is what? What is the data that we're storing here? It's important to keep that in perspective. What are we actually tracking? What are we using these B+ trees for? Go ahead.
Page numbers.
Page numbers. So we're using it as an index. The leaf nodes are going to have key value pairs, where the key is some value from the table, and the value is what page, what heap page that value lives on, right? And so we talked about a simplified, or maybe not simplified, simplified is the wrong word, a similar structure to a B+ tree called a B tree. And my argument last class was that B+ trees are more commonly used because they have certain advantages. So what are the advantages of having two kinds of node structures as opposed to just one node that holds everything, the data, the pointers, and all of it? What are the advantages? Does anybody remember? Yeah. We get a higher branching factor. So the search keys and the pointers take up less space than the index key value pairs. That's the idea anyway. So if we keep the internal nodes we can store more of the search keys and the pointers if we get the indexing values out of those internal nodes, which means we're going to have a larger branching factor, And that branching factor is important because that's where the performance comes from. That's what dictates how fast we're shrinking our search space. All right, let's cover a few more key terms and concepts for these B+ trees. K is a value that we'll use for something that's being searched for or inserted or deleted. I'm going to show you some pseudocode operations for interacting with B+ trees, so K is what we're going to be using. B is called the fanout, or that's actually the branching factor. Same thing, fanout, branching factor. It's the same concept. But what dictates this? How do I know what the value of B is going to be? Do I get to pick that value? As programmers, is that something that we choose? I'm going to make a B+ tree and I'm going to say this is the branching factor that I want? Or is there some other force at work here? Yeah.
Well, it seems like there's two things that can dictate what your fanout is. One is how many pointers you're going to assign to each node, and the other would be how many levels. I forgot that's the right term. I guess how many levels would be for your cluster.
Well, so I agree with your first point. It is a function of how many pointers I can fit in a node. I mean, that's basically the definition of fanout, is how many pointers do I have per internal node. But how do I know how many pointers I have, right? We've just kind of pushed the question down the road a little bit. Is that something that I get to decide? I get to say that each internal node has 4 children, and that's it? Or is there something else dictating what that value should be? Where are we storing our index in our database? Index gets stored how? Where do I store regular data in a database? In what structure? What'd you do for homework 1? Yeah. In a heap page, in a heap file, right? Same thing for an index. I'm storing it in a heap page, in a heap file. So I've got pages, and this tree structure actually works very nicely for us. One node is going to consume one heap page. It's a very natural way of representing nodes in our tree. I don't want to have my nodes split up across multiple pages. That's going to make it awkward for me to access that data. So one node is going to go into one heap page. So if I want to know what the branching factor is, it's really how many search keys and pointers can I fit in a single heap page. That's what's going to determine the branching factor for a B+ tree. How much stuff can I actually fit in there? So we're going to use, very small values because it's easier for us to do examples with smaller values for the fanout. But in practice, those values, we want them to be as large as possible. We want them to be big because, again, the bigger the branching factor, the faster we can find what we're looking for, the faster we're going to reduce that search space. So in practice, it would not be unusual to see fanout factors of 100 or more. Okay. Next, let's define some important properties. The number of elements in a node is dictated by the degree of the tree, which we're calling P. And so we've got 2 nodes to consider here. For internal nodes, the number of children that we have is defined, I'm sorry, I should rephrase this. There is a maximum number of children that we can have for an internal node. That's the same as the fanout. But the question here is, what's the minimum number of children that we're going to allow an internal node to have? What's the smallest number of children that we're going to allow an internal node to have? And traditionally, and for our examples, that's going to be fanout over 2. What this effectively means, right, is that for internal nodes, they need to be at half capacity or greater at all times. That means that sometimes there might be some empty space in these internal nodes, and the same thing's true for leaf nodes. But that's part of the benefit of storing our indexes in a B+ tree. Why? Why is it good to have some empty space laying around sometimes? What is the advantage of that? What was the big problem that we ran into when talking about indexes on Tuesday? Yeah. Insertions and deletions were a big problem with the indexing that we talked about on Tuesday. So the idea here is that if I leave some extra space around, that's going to make insertions easier. And it could potentially make deletions easier as well. So we want to allow our nodes to have some empty space, but we don't want them to be extremely empty because then that becomes inefficient as well. So the question is, what do we mean by empty in this case? And a traditional way of doing it is to say half capacity. I want every node to be at least half full at all times. At least half full. So for an internal node, that means it must have at least p over 2 children, where p is effectively the same thing as the fanout. So if the maximum number of children that I can have is 3, the minimum number of children that I could have would be 2. That is the smallest amount of children that I could have for an internal node. We also have search keys, right? So we can define search keys in the same way. If I have 3 children for an internal node, we saw this towards the end of class. Here is a node, right? It's got 3 children. How many search keys do I need to help me distinguish between these 3? 2, right? 1, 2. I need 2 keys to help me distinguish between 3 children. So if p is 3 for an internal node, I have to have at least 2 children, which means I have to have at least how many search keys in my node? I have to have at least 1. I could get rid of 1 child and 1 search key, and this node is still okay. It still satisfies that half capacity rule, right? This is an empty slot that if I perform an insertion or something like that, is going to help speed up that process. If I have a leaf node, we have the same concept, right? It's actually a little bit easier for leaf nodes because I don't have to worry about children. Makes the leaf node process simpler. A leaf node has no children, it just has values in it. So if p for a leaf node is 2, that means that it has to have at least 1 key in it at all times. If it goes down to 0, it's going to go away. Or maybe a better example would be if p is 3 for a leaf node. It would have to have at least 2 values in it at all times. If I remove 1, I've gone below half capacity, so I would need to figure out how to reorganize the tree to fill this node up or get rid of it. There's one exception to this rule, which is the root. There's one exception, which is the root. And so the root does not have to follow these rules. The root can be at less than half capacity. In fact, sometimes it needs to be. Consider if, in this case, right, if all I have is 1 node, that's the root, there's only 1 value in my tree, this node is at less than half capacity, and that's the only way that I can do this, right? There's no other way for me to make this work. Only 1 value in the tree. So this node has to be 2 empty. So we allow exceptions for the root, but every other node is going to follow this rule. Has to be at least half capacity. It should also be noted that the degree of the inner nodes and the children does not have to be the same. Think about what that means. I could use a different degree for, in fact, we will use a different degree for the internal nodes and for the leaf nodes. And there's a good reason for that. There's a good reason for that. Again, the leaf nodes are also stored on heap pages. And the data that's stored in a leaf node is a little bit different than the data that's stored in an internal node. So I just may not be able to fit as many items on a heap page in a leaf node as I could in an internal node. Or maybe the opposite is true. It depends on the data that we're actually storing. I know this is a tricky concept. We're going to go through a lot of examples today that will hopefully drive this point home. So let's talk about the processes that are going to be used on these search trees, on these binary B+ trees. Searching is an obvious one. We need to locate data. That's what an index ultimately is for, right? I want to find values, and I want to find values fast, very quickly. So this is the easiest one we're going to look at today. If you know how to do a search through a binary tree or any other kind of tree, you're not going to see any surprises here, right? I start at the root, and then I say, hey, is this a leaf node or an inner node? If it's a leaf node, then the value that I want is somewhere in there. If it's an internal node, then I need to figure out which path to take next. So I'm going to look at the keys. If k, the value that I'm looking for, is less than all of the keys, I'm going to take the leftmost branch. If it's greater than the largest key, k of q, then I'm going to take the farthest rightmost branch. And if it's in between, right, I'm just going to use the search keys to find the branch in the middle that satisfies that value. Notice that we are assuming, and therefore we must enforce in our implementation, that the search keys are stored in order. They're stored in sorted order. This doesn't work if I don't store my search keys in sorted order. And so once I find which internal node I'm looking for next, it's a recursive algorithm. I just call search on that next node, which is going to repeat this process. And then eventually I'll find the node, the leaf node that has the value that I'm looking for. Or actually, it may not find that value, right? It may find the leaf node where the value could be. That doesn't actually mean that the value is in the tree. It's possible for me to search for values that aren't actually even in the tree. Yeah.
Should we change the case more than P0 to case without equal to 0?
Less than or equal to 0? I believe you're correct. Yes, there does need to be an equal sign.
You don't have to change the value.
No, we do not. I mean, it could go either way, right? I could put the equal sign on the less than or the greater than, but I just need to be consistent about it. Depends on the tree. Depends on the implementation. That's an implementation detail. But you are correct. One of those would need to be an equality to satisfy the full range. Let's take a look at an example. Let's say I want to search for 8. So I start at the root. K is 8. I look at the root, I see a 7 in there. That's the only value. So 8 is greater than 7. That's going to tell me to go to the right. All right, and now I see another node, 9. It's still an internal node. I see a 9 in there. 8 is less than 9. That's going to tell me to take the left branch. All right, now I've made it to a leaf node. That means that the value that I'm looking for should be in that leaf node, and it is. It's right there. It's not a complicated process. What's the degree of the internal nodes in this example? What's P for the internal nodes in this example? What is P? Or what is the Fanout? The branching factor. That would be the same idea. What is that for that last example? Yeah, it's 3. I see a node with 3 children. That's the largest number of children that an internal node can have. That's the same thing as the degree. What's the largest number of children? That's P for a given node. If the children isn't the way you want to think about it, look at the search keys. I can hold at most 2 search keys in my internal nodes. So the relationship between search keys and the degree is +1. 2 keys plus 1 gets me 3. That's the degree of the internal nodes. What's the degree of the leaf nodes? Is it 3? That's what it was for the internal nodes. What's the degree for the leaf nodes? Well, we can take a look. So leaf nodes is just the number of keys. What's the max number of keys that I can fit in a leaf node? In this case, it's 2. They're not the same. They don't have to be the same. The degree for an internal node is 3 in this example. The degree for a leaf node is 2 in this example. They do not have to be the same. Any questions before we take a look at insertion next? Yes. Okay.
K is larger than KQ, I think it means that K does not exist. It's not in this tree.
I disagree. What if I'm looking for 12? KQ is just the last search key. 12 is greater than the last search key, which is 7. It's just telling me to go right. 12 is greater than 9, which is the last search key. It's just telling me to go right.
When we run this code, K is at 12 and node is 9. Node is 9. So K0 is
K0 in this example would be 8. Why?
no, 8. Node is 9, so we only have K0, which is 9.
We also have KQ, which is also 9. K0 is just the smallest search key in a node. KQ is just the largest search key in a node. If I only have one search key in a node, they are the same. No, it's the key, the search key. Yes, it's the search key. That's correct. Any other questions before we take a look at insertion? So searching's the easy part. Insertion is where things get a little bit complicated. You'll notice that the first step for insertion is a search. And I really want to emphasize this point, right? If you code up search the way that I've shown it on the slide, you can save yourself a big chunk of time with insertion because you can just do a search at the beginning. You don't have to retraverse the tree. Just call the search function to do that part. And then you're going to find the leaf node where the value should go. Where that value should go. And now you've got a decision to make. If the target node, the node where I want to put the value, is not full, that's the easiest possible outcome. I just put the value in the node and I'm done. If the target node, the node that I'm adding the value to, is full, then I have more work to do. I'm going to make a new node that contains half of the values of the old one. Or I call this a split. I'm actually splitting that full node into two nodes. Half the values go on one side, half the values go on the other side. And then the largest key from the new node is going to get passed up the tree. I have a new node now. I have to insert another search key into the internal nodes so that I can find that new node. Right? If I have a new node, a new leaf node added to the tree, that's going to require one more search key to be added to the internal nodes. But there's a problem that we could run into there as well. If I take a search key, I pass it up to the parent. If the parent's not full, then it takes the search key and we're done. But if the parent is full, then I have to do the splitting process again. I have to do that split on the internal node. It's going to look exactly the same. Half the values go to the left node, half the values go to the right node, and then I'm going to take the largest value from the new node, the middle key, and pass that up to its parent. And I have the same question. Is that node full or not? And if it's full, I'm going to do another split. Pass the key up the tree. So it can cause a chain reaction where I keep passing values up, keep passing values up, keep passing values up. Eventually, one of two things is going to happen. I'm either going to find an empty slot and I'm done, or I'm going to hit the root. If I make it to the root and the root is full, then I have to split the root as well. And then I'm going to make a brand new root that sits above those two split values. In other words, I've added a layer to my tree. The nice thing about this algorithm, remember that one of the qualities of a B+ tree is that it has to remain balanced. this algorithm actually ensures that it always will remain balanced. We don't need to do a lot of work, at least for insertions, to maintain the balance of the tree. It will naturally stay balanced if we follow this algorithm appropriately. Let's try it out. I think it's good to do some examples to really illustrate how this process works. This actually is about as far as we got in class at the end last time. It's the same exact tree, as a matter of fact. And so let me sketch it up here on the board so that we can work with it. 5. And then I've got 7 and 8. Okay. How many internal nodes do I have? 1, the root. I have 1 internal node. I have 2 leaf nodes. 2 leaf nodes. And I want to put a 3 in. So step 1 is what? I want to insert a 3. What's the first thing I do? Search. Figure out where that 3 should go. So I look at the key of the root. I say, 3 is less than 5. I'm going to go left. I see this node. It's a leaf node. I know it's a leaf node. So this is the node where I want to put the 3. But now we've got a problem. It's full. That node is full. It cannot hold any more values. So we have to do the split. We have to do the split. So I'm going to make another node over here. I now have 3 values that I want to put into 2 nodes, right? 1, 3, and 5. And I've got 2 ways that I could possibly do it. I could put the 1 and the 3 over here, and the 5 over here, or I could put the 1 over here by itself, and the 3 and the 5 in this node. Both ways are actually fine. You can construct a B+ tree that does it either way, and it will work just fine. The important thing is to be consistent. You have to be consistent. If I take the extra value and push it to the left this time, then I need to take the extra value and push it to the left every single time I do a split. I can't just arbitrarily choose to sometimes make this right node the bigger of the 2. Does that make sense? It doesn't matter which way you go, you just have to be consistent about it. And so I'm going to be consistent about it and always push an extra value to the left if I have one. If I have an extra value to deal with, I'm going to move it to the left. So 1 and 3 goes over here. Actually, I don't want to erase that yet. And this node's just going to have a 5 in it by itself. But I'm not done. I'm not done yet. You can see that my pointers are still messed up. This node's not attached to anything yet. So the next step says to take the largest key of the new node, or another way of saying that is look at all the values that you had, take the middle one, and push it up the tree. Take that middle value and move it up the tree. So I'm going to take this value of 3, and I'm going to push it up to, the parent, the closest parent that I have, right? I don't technically have a parent yet, but this one should be my parent. So I'm going to push the 3 up here. I now have 2 keys, 3 and 5. And now you can see that I have to redraw my pointers to reflect the fact that I have this extra node and this extra key. So I'll take these pointers and update them. And this is what the tree will look like once I have inserted that 3. Are there any questions? Yes?
So in the original model where you only have the 2 pointers, would that be considered branching factor of 2 or 3 because you could theoretically have a third pointer?
That's a good question. So I mean, the tree itself has a branching factor, like the tree as a whole has a branching factor, and that will always be the same for, so if in this case it would be 3 for the whole tree. If I look at an individual node though, and I want to know the branching factor of that particular node, then I could say that it's only 2 in this particular case. But we don't often talk about that. We usually talk about the branching factor on the tree as a whole. Good question. Any other questions? Okay, let's keep going. Let's do a few of these so we get the hang of it. So I've inserted the 3, and here's what it looks like. You'll notice it matches, right? Our diagrams match. Now I want to put a 12 in. I want to put a 12 into this. So first thing I do is I search. I look here. I say 12 is bigger than both of these values, so I'm going to go to the right. This is a leaf node, and this is now the node where I want to put the 12. But it's full. It's a full node. I cannot put the 12 here. So I have to do the process again. I've got 3 values, 7, 8, and 12. Again, if I have an odd number of values, I'm always going to take the extra one and keep it to the left. So this node is actually going to stay unchanged. This node's not going to change at all. And I'm going to make a new node that's got my 12 in it. But I'm not done, right? What has to happen next? I heard somebody say another split. Yeah.
You have to add the key to
I have to add the key. I have to move the key up. So what's the key? What's the key? What's the value that I'm moving up? Yeah. 8. 8 is the key. It's always going to be the one in the middle. 8 gets pushed up the tree. I want to put 8 here, but I can't. It's full. So I have to do another split. I have to split this node. I have to split this internal node. The splitting process is the same, actually, though, for both. It's really the same. So I'll split this node. I've got 3, 5, and 8. And so actually what ends up happening is I'm going to have another node over here with an 8 in it by itself because I have an extra value, so I'm going to keep that on the left. Keep that on the left side of the tree. What happens now? This is where things get a little tricky. Yeah.
You split, it's not really fair to say you split the root, but you no longer have one node.
I don't have a root. Yeah, that's a problem. I do not currently have a root. That's an issue that we need to deal with. And so let's see what the algorithm has to say about that. If the root needs to be split, create a new root with 1 key and 2 pointers. But what should that key be? What should that key be? 5. Because it's the middle one of these 3, right? I perform the split. I take the middle value. I push it up. Perform the split. Take the middle value. Push it up. So I'm going to have a new root. Unfortunately, I did not leave myself enough space for this. I don't want to redraw this whole tree, but I kind of do. Shoot. Should have planned better. I'll just squeeze it in. Here's my new root. It's got 2 children. And I still have to fix these pointers as well, right? This pointer is no longer going to go here. It needs to be balanced. The tree needs to stay balanced. I can't have 3 nodes on this side and 1 node on this side. That would be an unbalanced tree. This actually needs to go over here. And if I'm being honest, we actually did things a little bit out of order. I probably would have fixed these pointers before I created my new root. It all needed to happen. I probably would have fixed these up before making that new node and connecting it up to the tree. Yes?
Based on how this is working out, do we need to amend how we originally described the search to like say greater than or equal to or less than or equal to?
Yes, that's what we talked about earlier. Yep. That's what when we were talking about one of these has to be marked equal to earlier today. That is correct. I will update the slides with that as soon as I get out of class and get back to my office. And so here's what the tree looks like. Here's what the tree looks like. after we've added our new root. I've got 3 levels now. I've got 3 internal nodes, right, and 4 leaves. And so the next value that we want to insert is a 9, and you can see that the slide kind of spoils this one, but it's an easy one. This is the best case scenario. I want to put a 9 in the tree. So first thing is I do my search. 9 is greater than 5. 9 is also greater than 8. I find this leaf node, and there's an empty spot. That makes my life easy. Just plug the 9 in. Now I'm going to keep these in sorted order, so I'm going to scoot this 12 over. We always want to keep things sorted. Yes?
In the slides, that 5 on the second level is not there anymore. Do we need to...
Oh, I'm sorry. You're absolutely right. This is redundant. Yeah. Thank you for pointing that out. I missed it. When I push a value up the tree for an internal node, it literally means removing it from here and moving it up the tree. So I skipped a step. You are absolutely correct. Think about why we don't need this. If I take this branch and see a 5, I already know that I'm less than or equal to 5. So having that same search key here is not helping us. Or another reason why you can justify taking it out is look at how many children we have. I only have 2 children. I don't need 2 search keys to distinguish between only 2 children. I can do that with 1 search key. So you are correct. I should have removed this. Notice that we are going to have duplicates between search keys and actual values in the leaf nodes, though, and that's okay. I can see the same value show up in a leaf node and as a search key. That's fine. I do not want to see the same search key show up in an internal node more than once. That is a problem. That is a mistake. Great question. Any other questions? Any others? I think we got a couple more to play around with. All right. I like this one, actually. I want to insert a 6. And a lot of people, when they come across this problem, they want to insert a 6. Their eyes naturally gravitate to this node right here. They see that 5, and they're like, ah, there's an empty slot. I'm just going to put the 6 right in that slot. No. No, not right. Why? Yeah. 6 is greater than 5, so I should be going right at the root. I got to do the search, right? Got to follow the algorithm. The same process every single time. So I'm following this algorithm. I'm going right first. 6 is greater than 5. 6 is less than 8, so that's going to lead me here. It's full. I have to do some more work. I have to split this node. So what are my nodes going to look like? I have 2 nodes now. I'm going to let you guys tell me this time. 2 nodes. What values are going to be in this one? 6 and 7. Good. And then the 8 will go here. What happens next? Seven goes up. It's the middle value. 7 goes up. Thankfully, I have an empty spot here, so I don't have to split this one. I update this internal node with the new search keys, and now I just have to update my child pointers to point to these new nodes. And there we go. We've properly inserted the 6. Notice what that does, right? You might be wondering to yourself, it seems like a real waste to not use this empty space that was here, because the 6 could have gone there and it still would have had everything in sorted order, right? But actually, by putting the 6 over here, I have another empty slot over here. And remember that empty space is good. That empty space is going to make future insertions faster. So even though this insertion wasn't necessarily the easy kind, the fast kind, right? I still have lots of spots now that can insert values quickly. All right, that's the insertion example. Before we look at deletion, does anybody have any questions about insertion? I've got some practice problems that we'll do if we have time, so we can get more practice with these. I really want to hit these B+ trees hard. So any questions before we do deletion? Yeah. I'm sorry? Is it okay to store duplicates? So you have to be a little bit more specific, right? I've got leaf nodes, I've got internal nodes. So where are we storing the duplicates, I guess would be. I'm sorry, if I added another 6? Okay, so then that depends on what kind of index we've got. Am I indexing a column that has unique values, or am I indexing a column that's got duplicate values? If I'm indexing a column that's got duplicate values, then sure, I could insert another 6. If I'm indexing a column that's got unique values, what would I do? I would see that the 6 is already in the tree and be like, well, that's it, I'm done. I already have the 6. If I'm doing non-unique values, that actually changes the leaf node structure quite a bit. How would that change the leaf node structure? Would I see like 6 show up multiple times down here? That doesn't seem good to me. That would make searching difficult. What ends up happening is that along with, remember, what's not shown on this diagram, these are just the keys. These are just the search keys. I also have values, which are page numbers, in the leaf nodes. I don't draw them because they aren't relevant to the functionality of a B+ tree. But I have page numbers here, right? So 6 is on page number 101, maybe, right? And if I have unique values in the column, then that's all there's going to be, one page number. If I have duplicate, or if I'm allowing duplicate values in a column, then I would see additional page numbers here as well. So I would have a linked list of page numbers in my leaf nodes. For our purposes in this class, we oftentimes stick with unique columns just to make the B+ tree a little bit simpler. But it certainly can be done with non-unique values. Just have to have a linked list of page numbers instead of a single page number. Great question. Any other questions before we look at deletion? All right, let's do some deletion then. Here we go. I'm going to search for the node. It says where the new record should go, or where the new record should be, I think is a better way of saying it. Where the record that I'm trying to delete should be. I'm going to do a search. Once I find that node, I now have some options, right? If I remove that node, or if the node is more than half full, right, I can simply delete that value and I'm good. Remember, we have that lower threshold. Every node has to be at least half full. At least half full to satisfy our B+ tree conditions. So if I can remove that node, or if I can remove that value and the node is still half full, I'm done. But if I remove that value and the node is less than half full, I've got some work to do. I've got some options. The first thing that I'm going to try to do, if the node is less than half full, is look at my neighbors. Look to my left, look to my right. What makes this easier is the fact that, you'll notice, I treat my leaf nodes like a linked list, which is possible for me to do because I know my B+ tree is balanced. So I've got actual pointers going from one leaf to the next. So the first thing that I'm going to do is look to my neighbors and say, hey, do you have an extra value that I could have? And if they do, I'll take it from them. I'll take that value from my neighbor and use it. And then update the search keys accordingly. If my neighbors don't have enough values, they're also, close to half full, so they can't give me any information, then I have to merge. I have to pick a neighbor and combine those two nodes together into one node. It's the opposite of a split, right? If I'm inserting values, sometimes I have to split. With deletion, as my nodes empty out, sometimes I'm going to have to merge them back together. I'm going to have to fuse them back together. So I'll merge those values. I'll delete the entry that search key, because I have fewer nodes now, I need one less search key from the parent, and that might cause the parent to be too empty, in which case I might have to merge parents. I might have to merge internal nodes. Same process, right? Same idea. That process could cause a chain reaction. Merging internal nodes, sometimes we run into this. This is maybe the most complicated case of all the pieces of the algorithm that we've talked about so far. When I'm merging an internal node, you'll notice that the internal nodes are not connected directly. There's no direct connection between internal nodes on the same level. So I have to go through the parent. We call that push through. This is a bad example because I can't perform a merge with this particular tree, but I do have an example of this coming up on the exercises that we have. Basically, what happens is I go to the parent and say, hey, I'm looking for a value. The parent is going to go to the next child over, say, give me one of your values. So it gets passed up to the parent. And then whatever value was in the parent is going to be passed down to the original child. So it causes like a push-through effect. And it's really complicated to explain in words. It's better to see it with an example. So let's start an example. We'll get there. I'll show you an example. Here's our tree. This is not the same tree that we had before, unfortunately. So I'm going to erase this one and draw it up on the board real quick. 7, 1, 6, 9. And then I've got 5 leaf nodes. Okay. 1, 5, 6, 7, 8, 9, and 12. Now I just have to hook up the children, which is a little sloppy, but it's okay. All right, here's our tree. Actually, as one little side note I should mention, and I can show you this on the previous example too, it's a good thing to keep in mind. If I'm looking at a key, right? If I'm looking at a key in a internal node, this value is the largest value in the entire left subtree. Do you see that? I look at the 7, and what this 7 really means is that if I go all the way to the leaves of this subtree on the left, the largest value that you're possibly going to find is a 7. Same thing for these nodes, right? If I look at this 6 is saying if I go to the branch immediately to my left, the largest value I'm going to find in that branch is a 6. Doesn't matter how many layers deep you have to go. When you get to the leaf nodes, if you follow the path to the left, this key is telling you what the largest possible value could be. All right, anyway, let's delete some values. First thing I want to do is delete a 5. So I need to find where the 5 lives on the tree. We've done searching enough. We can skip through that part and understand that we're going to eventually get to this node. So I'll take the 5 out. Are we good? No? Why not?
Because we're consistently moving nodes to the left. We got to put the 6 where the 5 was.
Okay, sure. Are we good? Are we done? Yeah, we're good. We are. This node is still at least half full, right? It can hold 2 values. It's got 1 in it right now. That's okay. You can see these other nodes also have 1 value. That's half capacity. I need to be at least half full. This is exactly half full. This node is okay. This node is good. So I can say that I'm done. That's the easy part. If I delete a value and the node is still half full, I'm done. Easy. No worries. All right. I'm going to delete a 12. So I'll search, I'll find the node with the 12 in it, and I'm going to get rid of it. It's gone now. And now we've got some work to do, right? This node is no longer half full. It's completely empty. It doesn't matter if it's empty or not. It's less than half full, which is what really matters here. Less than half full. So the instructions say to do what? Let's go back a couple slides and see what the algorithm says. It says, if a sibling with the same parent is more than half full, take an entry from it. So I'm going to look to my sibling over here. I see, oh, hey, you've got an extra item that you could spare, right? You don't need both of these. You could survive with just one. So give me this one. So it's going to steal the 9. It's going to steal the 9 from its sibling. And then what needs to happen? Yeah.
The key in the internal node above it needs to be updated.
This key is no longer accurate. Has to be updated. It's now an 8. Again, the largest value in the leftmost subtree, which in this case is 8. That wasn't so bad, right? The borrowing or the stealing, whatever you want to call it, not so bad. Any questions about that part? Yeah. Well, I haven't been drawing them, but there are pointers here. They could. Could be doubly linked. Yeah, absolutely. I think it would make life easier if they were. Any other questions? Any other questions? Okay. We deleted the 5. We deleted the 12. All right, now let's delete the 9. All right, I find the node with the 9 in it, and I delete it. I'm empty again, right? Less than half capacity. The first thing I'm going to do is go to my sibling and say, hey, you got an extra value I can spare? But this time the answer is no. I don't. I do not have an extra value for you. So what this means is that we're going to merge. I'm going to merge these two nodes together. Merging an empty node with another node is a kind of a trivial activity. Keep in mind that if the degree of these nodes was higher, this node would not be empty, right? It would be at less than half capacity, but it would not be empty. The only reason that it's empty is because we've chosen a very small value for p for my leaf nodes in this particular example. But the case is the same. This is empty. I'm going to merge it with this node, which has the effect of this node going away entirely. It's gone. Are we done? Are we done? What do we think? Who thinks we're done? Who thinks we're not done? We're not done. We got more work to do. Why? It's unbalanced. That's true. There's another reason. I've got 3 nodes on this side and 1 node on that side. That's not balanced. There's another reason, though, that's telling us that we're not done yet. If I look at this node, what's the minimum number of children we can have? 2. And I've just got 1 now. I've just got 1. So this node is now less than half full. This node is now under capacity. Do you see that? It's now under capacity. So this is actually a case where we're going to do that push-through mechanism, which I think, again, is the most complicated thing to understand. This node does not have a direct link to here, but it is linked through its parent. So what it's going to do is it's going to say, I'm running low, right? I'm out of stuff. It's going to go to its parent and say, do you have any extra values that you could give to me? I can't go directly to the sibling. I have to go to the parent. Say, do you have any extra values that you could give to me? The parent is going to say, well, let me go to my other child over here and see if they have any extra values that they could give up. And it does, actually, right? This one could give up one of its values. So it's going to give up the 6, the largest one, to keep everything balanced. But what happens, I'm not just going to send the 6 over here. Do you see why that would be wrong? I can't just take this 6 and move it here. Yeah, it would mess up the ordering. I can't have a 7 on this side and a 6 on this side. That wouldn't work. It's not sorted properly. So we have to do what's called pushing through. I'm going to push this value through. I'm going to send the 6 up to the parent. The 6 is going to replace the value that was here. And the 7 that was here is going to pop out the other side and come down to this node here. Do you see how that works? I took the 6 and I pushed that 7 out of the root down to the other child node. Does that make sense? And now all of my internal nodes are happy. They're all at least half capacity. There's just one thing left that we have to do, which is what? I'm sorry? Yeah, the children, right? I have to update my child pointers. So not only am I going to pass this 6 up, I'm also going to pass the pointer to this node along with it, so that once this value gets here, I can update that pointer to this node now, and this node. Get this out of here so we can see this properly. And here's what the tree is going to look like once we're finished. All of my nodes are happy, right? They're all at least half capacity. My internal nodes all have at least 2 children. My leaf nodes all have at least 1 value in them. They're all satisfied. The tree is balanced. The keys are pointing in the proper way, right? 6, 6, 7, 7, right? That's probably the most complicated thing that could happen with that push-through process. Are there any questions? Yeah. What happened to the 8? That's a good question. You notice the 8 went away. I couldn't sustain it, right? In fact, the 8 would have gone away much sooner than when I actually erased it. As soon as I deleted this node, and I just had 1 child here, I had no need for that 8 anymore, right? There was no need for the 8 at that point. Or another way of thinking about it is I should always have 1 fewer search key than I have children. And so at the time, this node had 1 child, which means it should have had 0 search keys, right? And then we fixed that by stealing a search key from another part of the tree. Any other questions? Let's do a few more of these. Oh, let's do some exercises, actually. That's a better way of spending our time, I think. I've got a couple of these, I feel like. Yeah, I do. 1 for insertion, 1 for deletion. All right, we've got 20 minutes left. I want to get you guys some practice. Using a B tree with P inner equals 3 and P leaf equals 2. That is the same values of P that we use on this example. The exact same values of P. Don't think about that part too hard. It's the exact same values of P that we use on this example. Sketch the result of inserting these values. I'm going to give you 5 or 10 minutes, and then we'll spend the last 5 or 10 minutes of class going through this example to wrap up. Let me know if you have any questions. All right, I know you may not be finished yet, but I do want to go through this example before the end of class. And actually, before we do that, somebody asked me a great question that I wanted to talk to you about real quick before we start in on this example. If I look at this tree that we were working with earlier, what happens if I delete one more value, right? What happens if I delete one more value? It honestly doesn't even matter which one I delete. So if I pick one to delete, maybe like this 7, I'm going to get rid of it. And this is now half full, right? So I'm going to try to borrow, but I can't. They won't let me. There's not enough values here, right? So these get merged. This node goes away. This search key goes away. And now we have the same problem that we had earlier. So I'm going to go to my parent and say, hey, do you have another value for me? And the parent's going to go to its other child and say, hey, do you have a value for me? But this time the answer is no, I don't. I cannot do that push through in this example. So what has to happen now? Yeah.
You have the remain that the child now has to become the new parent node, like the new root node. The child of one has to become the new root node.
This has to become the new root node? I mean, it depends on how you look at the problem, right? I can keep this as the same root node, but no matter how I think about it, these two nodes are gone. I can't sustain them anymore. I cannot sustain them anymore. Think about why. I've got 3 leaf nodes. I can't have 3 internal nodes used with 3 leaf nodes. It's too many internal nodes. I can sort between 3 leaf nodes with just 1 node, right? I only need 1 node to distinguish between 3 leaf nodes. I did not have enough to sustain this second layer, this second level of the tree, so it's gone. And that's what happens with deletion. Eventually, you'll delete so many values that you have to end up removing an entire level of the tree. If all of my leaf nodes, right, are at the minimum possible capacity that they can be, the next time that I delete a value, I'm going to lose a level, an entire level of the tree. And now this works out nicely. I connect my root to the remaining nodes. I have to update my keys. 1, 6. And this is what my tree looks like now. All right. Let's actually do the example. I think we've got just enough time to get this done. First thing I want to do is insert a 9. So what do I have to do? What kind of node am I creating right now? This is a leaf node. This is a leaf node. Right? It's the only node. It's a leaf node, for sure. All right, I want to put in a 4. That's easy. I've got an empty slot here, so I can put my 4 in this node. When I want to insert the 12, that's when things start to get a little interesting. So I want to put the 12 in. Obviously, I'm out of space, so I'm going to create a new node. How do I have 4, 9, and 12, right? How are those values split across these 2 nodes? How are they split? The 4 and the 9, are they going to stay where they are, or am I going to move the 9 over here?
I'm saying, like, in this particular example, I do one thing, but if I just refresh, does it matter as long as we stay consistent?
It does not matter as long as you stay consistent. However, I get to define the consistency because I'm in charge here. Keep the 4 and the 9 over here, right? It's technically not wrong to put the 9 over here, but I'm going to stay consistent with all of my examples. I'm going to expect you to stay consistent on the homework assignment because it makes it much easier for me to grade, right? So keep the 9 over here. Keep that extra value on the left, and then the 12 goes here. What else do I have to do to finish this up? I'm going to push a value up the tree. Which value? 9. So I don't have a root, but I can make one. And it's going to have a 9 in it. All right, we're good. Next thing I'm going to do is insert a 7, okay? So I do the search. I want the 7 to go here, but it can't. It cannot go here. So I have to make another new node. What's going to go in this node? 4 and 7. That leaves the 9 for this node. All right, what's next? What do I do now? Push up the 7. I look at these values, pick the one in the middle, and push it up. So now I've got 7 and 9, and then I just have to make sure that my node pointers are up to date with the search keys. So something like this. 4, 7, 9, 12. Search keys match up, right? Everybody's happy. Okay. Next, I'm going to insert a 2. So I follow the process. I want to put a 2 here, but it's full. So I need to make a new node. Actually, I can see the future, so I'm going to make this new node a little bit lower. What values are going to go in here? 2 and 4, which leaves the 7 to be here. Right? This node is gone now. What happens next? I pass a value up. I take this 4, and I pass it up to the parent, but uh-oh. The parent is full now. The root is full, so I have to split this one. I'm going to have, let me just put my 9 and 12 down here, make some space for this tree to grow. Okay, so there's no room for the 4 here, so I have to split it. What's going to go in this one? Just 4. Just 4? It's a little bit different with the internal nodes, right? It's a little bit different. 4 goes here. What goes in this one? 9. So where'd the 7 go? Up. If I'm splitting an internal node, I take this value and I send it up, and I don't keep a copy of it here. That's a difference between a search key and these. I don't want to lose this 4 in my leaf nodes, because that's an actual index value that I want to be able to find, right? But a search key, I only want this number to show up once. I only want the 7 to show up once. So I don't want to have a duplicate of it. So I push it up. My root now has this 7 in it with those 2 as children. That's got 2 children. That's got 2 children. Are there any questions about that process? This is what it would look like after we did the 2. This is what the tree looks like. How are we doing on time? Oh, we're okay. So if I want to do the 6, that's an easy one, right? 6 is going to go here. If I want to do the 1, I got to split this node. 1, 2, 4. This node here now has 3 children, right? So what's the contents of this node going to be? 2 and 4. Update my child pointers. I want to put in a 3. Where's the 3 go? Do I have to do a split? No, actually, because it's going to go in this node right here, and there's room for it. And last, I have a 10. Do I need to do a split? Nope. Here is what the final tree would look like for this example. Yes? Oh, you're correct. Thank you. Sorry about that. I did the exact thing that I said not to do. This is the proper tree. Thank you. We still had a spot for it. I just picked the wrong one. I want to keep doing these exercises. We didn't get to the deletion exercise. We don't have time. I'm going to do the deletion exercise at the beginning of next class because I think it's important to do those concepts. We might even do one of these with the different degrees because, spoiler alert, I love asking questions like that on exams. So I really think you should get some practice doing those kinds of examples as well. We're going to do a lot of these. I want you to get this stuff down. So have a great weekend. We'll talk about this more on Tuesday.